90% of all life on Earth once disappeared. Entire oceans became toxic wastelands. Vast continents turned barren. In a cosmic blink, the planet was remade into a tomb. This was the absolute edge of annihilation for life itself. 251. 9 million years ago, and its true name speaks to the scale. The Great Dying. 96% of marine species vanished. On land, 70% of vertebrate species were erased, along with entire orders of the planet's most resilient insects. Forests withered. Reefs, which had thrived for eons, disappeared for 14 million years. What power could cause destruction on this scale? And what kind of thriving world existed before it, only to be erased? From the remnants of that lost epoch, a forensic investigation begins. We will trace the relentless scientific quest to pinpoint the primary cause of Earth's most severe extinction, follow the multi-stage cascade of environmental collapse it triggered, and understand precisely how life was pushed to the edge of annihilation. Every clue is etched in ancient rock, a planetary murder mystery, cold for 250 million years. And it begins with the victim, a world that, by every measure available to it, looked invulnerable. At the heart of that world lay a single immense landmass, the supercontinent Pangea. Its colossal presence fundamentally reshaped the planet, diverting global ocean currents and nutrient flows, creating vast isolated marine basins. On land, its sheer size engineered extreme regional climates. Deep in the interior, far from any moderating ocean, arid deserts stretched for thousands of miles, while coastal zones ran to monsoon. This configuration forged a world of stark environmental contrasts, a biosphere unlike any we know. And within it, life had not merely survived, it had flourished. But Pangea's geometry carried a hidden liability, and it would matter enormously. A single ocean wrapping a single continent produces sluggish circulation, fewer coastlines to steer currents, less temperature contrast between poles and equator to drive the deep water conveyor. The late Permian world was already a warm one, already running an ocean that mixed reluctantly, already edging toward oxygen-poor water in its quieter basins. The planet, in other words, was not resting at a comfortable midpoint when the crisis came. It was leaning toward the cliff before anything pushed. Beneath the Permian waves, marine ecosystems were exceptionally rich. The last great trilobites, their segmented bodies armored against the currents, scoured the seafloor. Intricate rugose and tabulate corals built elaborate reef systems that provided habitat and sustenance across the global ocean. Filter-feeding blastoids and stalked crinoids, often mistaken for plants, swayed in gentle currents, capturing microscopic nutrients. Countless brachiopods, shelled like clams but biologically distinct, dominated the seafloor in sprawling communities covering vast areas. From microscopic plankton to towering crinoid forests, this was the undisputed pinnacle of Paleozoic marine life, an era of deep time stability, seemingly invulnerable in its ancient rhythms. On the land above, an equally astonishing diversity had taken root. Vertebrates had undergone an immense evolutionary radiation, establishing elaborate food webs across Pangea's interior. Early reptiles thrived in an array of forms, from nimble predators to lumbering herbivores. Alongside them moved the synapsids, tenacious, mammal-like creatures, direct ancestors of every mammal that would ever live, ourselves included. They foraged beneath towering, damp forests of giant ferns intermingled with dense stands of primitive conifers. Ecosystems were not merely diverse, they were deeply interwoven, refined over countless generations. For its inhabitants, this world must have felt boundless and eternal. It is the crucial baseline, the peaceful portrait against which we must measure everything that follows. Unlocking this cold case demands a forensic science of deep time. To reconstruct events from 251, 9 million years ago, when the only witnesses are layers of rock, scientists must decipher faint geological echoes. Every fossil fragment, every chemical trace, every sediment layer a potential piece of evidence. But the vastness of geologic time constantly threatens to blur cause and effect. How could investigators pinpoint the precise moment a world began to collapse, or chart the terrifying speed of its unraveling? The answer lies at Meishan, in China, where the layered record of a shallow Permian Sea preserves the transition in extraordinary detail. Thin volcanic ash beds laid down by ancient eruptions provide the crucial timestamps. Within them, researchers isolate microscopic zircon crystals containing a mix of uranium and lead. Because uranium decays into lead at a known rate, the ratio of the two isotopes turns each grain into a clock, dating the surrounding sediment with astonishing precision. And within those meticulously dated layers, one fossil marks the boundary itself, a tiny eel-like marine organism called a conodont, Hindiodus parvus, whose sudden global appearance signals the exact horizon where the Permian gave way to the Triassic. Ash and animal together give us a stopwatch for catastrophe. What that stopwatch revealed was startling. For decades, the assumption had been that a die-off this comprehensive must have ground on for millions of years. A slow, grinding decline. High-precision dating demolished that idea. The main marine extinction pulse was compressed into roughly 60,000 years. Scientists have since dated its start to 251, 941 million years ago, and its end to 251, 880 million. Though the honest figure carries an uncertainty of some 48,000 years, and later refinements have argued for an interval shorter still. Even at the outer limit, the meaning is unambiguous. Whatever did this acted fast enough to destabilize the biosphere before the majority of plant and animal life had time to adapt. Ecosystems built over hundreds of millions of years were shattered in a geological instant. The record also shows the assault was not a single blow. It came in distinct pulses of devastation, each successive wave extinguishing any flickering recovery and pushing life further toward the abyss. This pulsed structure implies escalating, interlocking stressors, each amplifying the last, with no breathing room in which resilient species could rebound. And the pulses did not fall evenly. Different groups died at different moments. The gap between the collapse of some ostracods and some brachiopods has been measured in hundreds of thousands of years. And the land and the sea appear to have been struck out of step, with the terrestrial crisis in some regions running longer and beginning earlier than the sharp marine pulse. This matters because it rules out the tidiest explanations. A single instantaneous blow kills everything at once. What the rock shows instead is a staggered sequence, a system failing subsystem by subsystem, the collapse propagating through the biosphere along the connections that once held it together. The first hard evidence of what drove it came not from bones, but from chemistry. It came from carbon. The isotopic signature imprinted in rock layers across the globe reveals dramatic, rapid disturbances to the planet's carbon cycle, a planetary heartbeat gone abruptly arrhythmic. These anomalies, unlike anything in the preceding tens of millions of years, arrived alongside startling evidence of oxygen depletion in the ancient seas. Vast stretches of once vibrant ocean sediment showing the signature of water starved of the gas essential for respiration. A broken carbon cycle and suffocating oceans. Together, they were the first unmistakable signal of a planetary-scale catastrophe. and they pointed away from the seafloor entirely toward the continental interior. Before following that trail, it is worth noting where it does not lead. The obvious suspect, the one that would end the dinosaurs 186 million years later, is an asteroid. And for years, researchers hunted for one. They found nothing. There is no global iridium spike at the Permian boundary of the kind that betrays the Chicxulub impact, no confirmed crater of the right age, no shocked quartz layer that survives scrutiny. Claims have surfaced periodically and none has held. Whatever killed the Permian world was not delivered from space. It came from inside the planet. The trail leads to the frozen landscapes of modern-day Siberia. Beneath layers of Permian sediment lies a sprawling expanse of dark igneous rock, the Siberian Traps, a solidified ocean of basalt covering millions of square kilometers. These were not singular explosive peaks like Vesuvius. For hundreds of thousands of years, the crust simply fractured across a region now spanning some 2 million square kilometers. And basaltic lava flooded the surface through deep fissures extending miles into the mantle. Millions of cubic kilometers of molten rock surged outward. The region became a sterile black desert. The numbers resist intuition, so try this. The lava that poured out of Siberia would have been enough to bury the entire continental United States to a depth of hundreds of meters. In places, the basalt is stacked more than 3 kilometers thick, and it accumulated not in a single spectacular event, but in flow after flow after flow, some individual eruptions lasting for years, the whole province building over the better part of 1 million years. There was no explosion to witness, no mushroom cloud, no single day on which the world ended. If you had stood on Pangea and watched, you would have seen only a distant haze in the sky, a strange color to the sunsets, and rain that killed the crops. The apocalypse arrived at the pace of geology, which is precisely why nothing could outrun it. But the lava was never the killer. The rock is only the silent witness. The true agent was what the eruptions vented into the sky. And the reason they were so uniquely lethal lies in what the magma passed through on its way up. Beneath the Siberian basins lay massive buried coal measures and oil-rich strata. As the fissures tore upward, they acted as natural injection wells, cooking those carbon-rich deposits from below. The geology itself became a refinery. Thousands of gigatons of hydrocarbons were vaporized, forcing concentrated pulses of carbon dioxide, methane, sulfur, and toxic combustion byproducts into the atmosphere. This is the crucial point. The Siberian Traps did not kill the Permian world by erupting. They killed it by setting fire to a continent's worth of fossil fuel. There is a rival explanation for the carbon, and it is stranger still. One team has argued that the volcanoes were merely the trigger and not the weapon, that the Siberian eruptions flooded the oceans with nickel, and that nickel was the missing nutrient for a single-celled microbe called methanosarcina, which had recently acquired, by a chance transfer of genes, the ability to convert organic carbon into methane with unusual efficiency. Fed the nickel it needed, the argument goes. This microbe bloomed across the world's oceans and belched the methane that broke the climate. Nickel spikes do appear in the rock at the right moment. The hypothesis remains contested, and most researchers still favor the burning coal. But it raises a genuinely unsettling possibility that the worst catastrophe in the history of complex life may have been finished off by pond scum. Whatever the precise mix of sources, the scale of the injection can now be measured. Reconstructions of atmospheric carbon dioxide, drawn from the isotopic chemistry of fossil land plants in southwestern China, show levels climbing from roughly 400 parts per million in the latest Permian to around 2,500, a near six-fold increase, accomplished in about 75,000 years. Estimates put the total carbon injected into the ocean atmosphere system at somewhere between 3,900 and 12,000 gigatons. There is no parallel for this in the preceding tens of millions of years of the geological record. The Earth's thermal energy budget was fundamentally recalibrated. The planet responded exactly as physics demands. Sea surface temperatures climbed by something on the order of 10 degrees Celsius, a rise beginning before the extinction and continuing deep into the early Triassic. That is not a manageable drift toward a warmer baseline. It is a thermal shift that pushes marine physiology past its breaking point. In the shallow, sunlit seas where life was most vibrant, enzymes stalled, metabolic rates failed to compensate, and the basic chemical reactions of survival sputtered out. The tropics may have become effectively uninhabitable for many animals, a dead zone of heat straddling the equator. But the heat did more than cook. It shut down the ocean itself. Normally, cold, dense, oxygen-rich surface water sinks, driving a global conveyor that ventilates the abyssal plains and cycles nutrients from the depths back to the surface. Warm the surface enough and that engine stops. A hot, buoyant layer sits on top and refuses to mix, locking the ocean into rigid stratification. Without the downward transport of oxygen, the deeper layers, where trillions of specialized organisms lived, became a suffocating trap. Oxygen levels plummeted toward zero, and the biological foundation of the deep sea collapsed. Creatures like the crinoids and complex brachiopod communities that had thrived in those quiet depths for epochs died en masse, and their decay only compounded the crisis, consuming the last traces of oxygen and accelerating the descent into a planetary dead zone. We read this directly in the rock. Layers of dark organic-rich shale deposited across global basins, documenting a time when the seafloor became a graveyard. And then the conditions in the deep turned from merely suffocating into something actively lethal. In the stagnant, oxygen-free zones, anaerobic green sulfur bacteria thrived. These organisms metabolize sulfate, and the waste product they release is hydrogen sulfide, a gas highly toxic to almost all complex life. As dissolved sulfide intensified, the chemistry of the deep ocean turned corrosive, preventing any aerobic life from descending and trapping survivors in a narrowing corridor near the surface. In the worst affected basins, the concentration grew so extreme that hydrogen sulfide bubbled upward, escaping into the atmosphere as a dense, sulfurous vapor. Heavier than air, it would have hugged the coastlines of Pangea, poisoning terrestrial life already reeling from the heat. The ocean had begun manufacturing its own poison. While the depths were being poisoned from below, the surface waters faced a chemical attack from above. As the oceans absorbed the atmospheric carbon injection, seawater reacted with it and pH fell sharply. For the calcifying architects of the Permian, the brachiopods, crinoids, and rugose corals, the sea became a chemical hazard. Their shells and skeletons, fashioned from calcium carbonate, grew chemically unstable and dissolved into the rising acidity. This was a structural failure on a planetary scale. The seafloor transformed from a vibrant cradle into a dissolving graveyard of calcium fragments. The same chemistry fell on the land as rain. Volcanic sulfur reacting with atmospheric moisture generated a corrosive downpour across the interior of Pangea, and the terrestrial world shifted almost overnight. Soils, once the lifeblood of ferns and early conifers, were leached and stripped of nutrients. Root systems failed as groundwater turned toxic. This was not merely a loss of green canopy. It was the destruction of the planet's primary carbon sinks. removing the very machinery that might have drawn the excess carbon back down. As vegetation died back on a continental scale, the protective covering of the Earth vanished, leaving soil vulnerable to unchecked erosion. Vast landscapes turned into raw, scarred terrain. The devastation of the forests left a signature so strange it took decades to interpret. In Permo-Triassic rocks all over the world, at precisely this horizon, the pollen and spores of trees nearly vanish, and in their place the record fills with the remains of fungi and algae. This fungal spike is what a planet's worth of rotting biomass looks like from 250 million years away. The decomposers inheriting a world of dead wood. Nearly all the world's trees appear to have died at once, and the spores that do survive carry something worse. Across multiple sites, fossil pollen and spores from this interval are found malformed, mutated, unseparated, structurally deformed at rates far above any normal background. The leading explanation is radiation. The same volcanic emissions that acidified the rain also released halogen compounds capable of destroying stratospheric ozone, stripping away the planet's shield against ultraviolet light. If so, then to everything else the biosphere was enduring, we must add a sky that had begun to burn the life beneath it, damaging the reproductive machinery of plants themselves. The warming then triggered a hidden reservoir. Beneath the seafloor lie methane clathrates, cage-like structures of ice trapping vast quantities of frozen gas. As ocean temperatures climbed, this icy foundation reached its thermal limit and dissociated, venting immense pulses of methane into the water and eventually the air. Methane is a greenhouse gas far more potent than carbon dioxide, and its release created a compounding thermal effect. Warming begetting more warming, locking the planet into a runaway state. What began as a volcanic event had become a self-sustaining feedback loop that no longer needed the volcano. The fingerprints of the burning continent traveled with it. Mercury, vaporized from those cooked sediments, appears in the rock record worldwide at exactly this interval, a global marker confirming the dispersion of Siberian volatiles across the entire planet. As the metal settled into water and soil, it worked its way into the food chain, poisoning survivors and triggering reproductive failure across whole populations. This was not one disaster, but a multifront assault. Thermal, chemical, and atmospheric systems failing simultaneously, each one closing an escape route the others had left open. Nothing was spared, including the group that usually survives everything. The Great Dying remains the most devastating extinction in the entire history of insects, the only one they ever suffered, claiming 8 or 9 entire orders and pushing 10 more to the edge. For millions of years, these hyper-specialized creatures had occupied every niche of the Pangean landscape. From the damp undergrowth of giant ferns to the air itself, their near-total disappearance signals that the toxicity saturating the atmosphere and soils left no refuge at all, and it stripped the world of pollinators and decomposers, the small engines that drive ecological renewal. Plants that depended on them could no longer set seed. The collapse had reached the reproductive cycle itself. On land, the toll can be counted in lineages. 70% of terrestrial vertebrate species vanished, and with them roughly 78% of genera, not just individual species trimmed away, but whole branches severed. Among the casualties were the gorgonopsids, saber-toothed, powerfully built synapsid predators that had ruled the Permian landscape for millions of years, the apex carnivores of their world. They had no successors. In the rich fossil beds of South Africa's Karoo Basin, where the transition is preserved layer by layer, you can read the sequence directly. A diverse, crowded community of specialized herbivores and predators, then a chaotic interval of dying, then a scrubby, impoverished landscape dominated by a single stubborn survivor, an entire ecosystem, compressed into a few meters of rock. The scale of erasure is easiest to see in what stopped being built. Before the extinction, calcified reef systems had been a fixture of the planet for tens of millions of years, the structural foundation of entire marine communities. Then reef construction simply stopped. Ocean chemistry had shifted so violently that the organisms responsible, sponges, corals, bryozoans, became incapable of precipitating the minerals they needed. For 14 million years, no new reef systems formed anywhere on Earth. It is an enormous, silent void in the record, an interval in which the planet's primary architects of biodiversity were absent. The land records the same absence in a different medium. For millions of years into the Triassic, there is a coal gap, a stretch of deep time in which the Earth laid down almost no coal at all, because there were scarcely any thriving forests left to become it. There is a chert gap, too. The silica-rich rock built from the skeletons of microscopic marine organisms simply stops forming because the organisms that made it were gone. Consider what that means. 3 vast independent archives, reefs, coal, chert, each recording a different biological process in different environments on different continents, built by unrelated organisms. All 3 switch off at the same horizon. All 3 stay off for millions of years. This is the signature that separates a mass extinction from a bad century. Not that many things died, but that the planet's basic manufacturing processes stopped simultaneously and stayed stopped long after the killing itself had finished. So how did anything endure? The survivors reveal a brutal logic. In this hollowed-out world, one animal emerged as protagonist. Lystrosaurus, a squat, pig-sized synapsid whose success owed nothing to speed or ferocity and everything to raw, unremarkable utility. With a barrel chest and a powerful, shovel-like beak, this herbivore bypassed the refined dietary requirements of its extinct cousins, feeding on whatever harsh, scrubby vegetation could root in poisoned soil. In some regions, Lystrosaurus populations swelled until they accounted for as much as 9/10 of all terrestrial vertebrates, a singular, monotonous landscape where nearly every living movement belonged to one genus. It was not alone, but the surviving cast was fractured and desperate. Sharks, already ancient masters of the marine realm, relied on generalized feeding to scavenge across shifting, low-oxygen seas. Small, resilient reptiles endured in localized refugia that escaped the worst of the poisoning. Among the insects, the orders with underground or aquatic larval stages found narrow sanctuary from a scorched surface atmosphere. This was not a triumph of strength, but of niche preservation, of being small, unfussy, and lucky enough to be somewhere the catastrophe reached last. These scattered remnants represent a genetic bottleneck so narrow that the entire trajectory of the planet's future rested on them. Every lineage alive today, including our own, traces its pedigree through that filter. Recovery, when it came, was not a burst of vitality, but a fitful crawl lasting millions of years, an evolutionary dead zone far longer than the rebound after any later extinction. The Earth remained trapped in chronic environmental fatigue. Recurring pulses of sulfur and carbon lingered in the atmosphere and oceans, suppressing the return of complex communities. Shallow seas, once centers of biodiversity, were reduced to microbial mats and hardy generalists enduring stagnant, oxygen-poor water. On land, acidified soils and stripped nutrient cycles left arid, inhospitable plains where forests had stood. Evolution was forced to restart from a fractured, narrowed genetic base, stripped of the specialized niches that had defined the previous epoch. The survivors themselves record the stress in their bodies. Across the boundary, lineage after lineage shrinks, brachiopods, gastropods, bivalves, foraminifera all appearing in the early Triassic as miniaturized versions of their Permian ancestors. Paleontologists call it the Lilliput effect, and it is what a biosphere looks like when there is not enough oxygen, not enough food, and not enough time. Growth is stunted, maturity comes early, and being small stops being a disadvantage and becomes the only viable strategy. For millions of years, the world was inhabited by dwarfs, and in the shallow seas, something genuinely eerie happened. With the reef builders gone, and the grazers that normally kept them in check wiped out, microbial mats and stromatolites spread across the seafloor. Structures that had dominated the oceans more than 1 billion years earlier, in the Precambrian, before complex animals existed at all. For a geological moment, the Earth's shorelines looked as they had before the Cambrian explosion. The planet had not merely lost its diversity, it had regressed, briefly, to a much older and simpler version of itself. The deep ocean held the memory longest, even after surface environments showed signs of stabilizing, dense, stagnant bottom waters prevented the recolonization of the seafloor. Without vertical mixing, the engine of marine productivity, the cycling of nutrients from the abyss back to the surface, remained crippled, and the food web could not support high metabolism predators or deep water specialists. While surface life incrementally diversified, the abyss stayed a desert, a silent reminder that the geochemical system had been pushed too far to snap back. Only as oxygen levels slowly rose did the oceans finally shed the last suffocating shadow of the Permian. Why so long? The answer is that an ecosystem is not a collection of species but a network of relationships, and the relationships take far longer to rebuild than the organisms. A reef is not coral. It is coral plus the grazers that keep it clean, plus the predators that keep the grazers in check, plus the currents that feed all of them. Kill enough nodes and the surviving species inherit a world in which none of their instincts work. Prey with no predators, predators with no prey, plants with no pollinators. Complexity has to be reassembled from the bottom, one functional layer at a time, and each layer must be stable before the next can be built on top of it. That is why the Earth spent millions of years as a place of microbial mats and stunted dwarfs. It was not waiting for evolution to invent new animals. It was waiting for the food web to exist again. And when the world did restart, it restarted as something else entirely. The void left by the dying Paleozoic lineages acted as a vacuum, favoring organisms that could handle a volatile, oxygen-poor climate. Into it moved the archosaurs, agile, fast-moving reptiles whose descendants would become the crocodiles, the pterosaurs, and the dinosaurs. Their advantage is thought to have been respiratory. An efficient, flow-through lung architecture of the kind birds still used today, capable of extracting oxygen from a thin, depleted atmosphere that left their rivals gasping. While other lineages faltered in the low oxygen pockets of the early Triassic, archosaurs surged across the empty Pangean interior, colonizing vacant niches and setting an evolutionary trajectory that would define the next 150 million years. That is the deepest irony of the Great Dying. The synapsids, the mammal-like animals that had dominated the Permian, our own direct ancestors, survived the catastrophe, but they never got their world back. Lystrosaurus inherited an empty planet and then lost it, ceding the stage to the archosaurs for the entire Mesozoic. Our lineage would spend the next 180 million years small, nocturnal, and marginal, waiting for another asteroid to clear the board again. The Great Dying did not merely kill 90% of life. It reassigned the future, which leaves the uncomfortable part. The Great Dying killed not simply because of the carbon released, but because of the speed at which it overwhelmed the planet's capacity to absorb it. The oceans acidified because the input outran every natural buffer. The climate broke because the carbon arrived faster than weathering could draw it down. And the Siberian traps took on the order of tens of thousands of years to inject their thousands of gigatons. Human industry is currently moving carbon into the atmosphere at a rate that, year for year, some researchers estimate exceeds even that. Where the traps surged over millennia, we are producing a near vertical spike in the geological record. This is why the end Permian is studied with such intensity, not as a distant horror, but as the closest natural experiment we have for the direction we are pushing the planet ourselves. The rock at Meishan is only a few meters thick. In that narrow band of stone sits the record of a world that had every advantage: complexity, diversity, hundreds of millions of years of refinement, and lost all of it in less time than separates us from the last ice age. The Permian biosphere was not fragile. It was the most sophisticated the planet had yet produced, and that sophistication was precisely the problem. A rigid, highly specialized food web cannot bend when its foundation is incinerated. The Great Dying stands as the ultimate proof that planetary systems have thresholds, that crossing them is a matter of rate rather than magnitude, and that the recovery is measured not in centuries but in tens of millions of years. Life did not merely survive it. Life was rebuilt from the few, unremarkable survivors who happened to be tough enough, small enough, and lucky enough to still be standing when the silence finally lifted.